Hello, Riley. There?
Hi, can you hear me?
Yeah, yeah.
Great.
You said your internet is not stable today, huh?
It has not been, no. It's been going through some periods, so it was good for an hour, and then my wife started her class, and then it just kept going on about every 10 minutes or so. And sometimes it would stay out for a little while, sometimes not so much, but um, it's unpredictable right now.
Yeah, yeah, yeah.
So,
Okay, yeah. You can always use the recorded lecture, I guess.
yeah, I have a hotspot on my phone, like if it's an emergency, but I don't have
Sure,
unlimited data or anything, so I'm trying to save that for
sure.
like quizzes or things like that on my classes.
Mhm, mhm.
I don't think it's necessary, but I'd rather be safe for when I need it.
Yeah, yeah, I understand. Are you back home or in Carbondale?
I am in Carbon. I mean, I live here with my wife, but um,
Okay. So this issue is probably Carbondale internet.
I'm sorry. Could you say that again?
The issue must be the Carbondale internet then, right? Do you have Mediacom or from?
Yes, it is MediaCom. Yes. So I've had them look at it actually twice, and neither of them found an issue. So, like I said, it comes in spurts. So I went the first 3 months we lived here. We did not have good, reliable internet. And then we went for about a year and it was pretty good. And then every now and then it just goes in and out. So it'll be a few months good and then just a couple of weeks really bad.
Yeah, I know. Yeah. Hello, Christian.
They're tradition.
Yeah, you're back. Hey, Gordon.
Sorry,
Hey,
Bowden, you'll be by yourself today.
yeah. Hey, Christian, real quick, before class starts, on computer science, it was actually correct that the arrow was on the other side, correct? I'm not insane,
At
right?
the which one?
So someone in class pointed out that the arrow should have been on the right side, not the left side of the.
Yeah.
Okay,
Yeah.
I was pretty sure. I even went through it in my notes. I'm like, no, the truth table would be so different. But the teacher was just like, no, it's right, and
Yeah.
didn't say
And
anything else.
well, she was saying like the computer logic isn't a direct translation of the English, but then she was using a direct translation of
Right,
the English.
exactly. Yeah, that's why I was like, then stop translating.
Right. Because yeah, I mean logically it would definitely go the other way. Like if you were programming something.
Right,
Yeah.
absolutely. Yeah, because you need the conditions first and then the result, and she was just putting the result first. So okay, I'm happy I'm not insane, but I felt like
Yeah. I mean that was just one of those things where it was like you need a better English sentence that you could actually like put into a program and
right.
explore, I guess. It was just kind of yeah.
I thought it was a great example of you can't literally translate English into the programming logic, but she was literally translating into it. So I was like, oh, come on.
Yeah, it seemed like that's what they were going for, but I don't know if she got that straight out of the book or not. So I just kind of, I
I
understood it. I understood
yeah.
both sides of the argument, I guess.
Yeah,
But
but I did the truth table and it doesn't come out the same.
see, that's something that you could probably bring up because I didn't do the truth table. So you
Well,
should probably,
okay, so I was curious. I was like, okay, am I insane or is this actually a thing? And the truth table comes out true, true, false, true. And the truth table that she gave us for the implies was true, false, true, true.
Mhm.
So the truth table that she gave us for that condition was not in coherence with the truth table she explained with her sentence.
Right.
So, all right, I figured you knew enough that, but I didn't want to make like a big scene.
Yeah. No, I definitely understood the argument, and but what I was confused was that she was basically arguing for your guys' side, but then was saying that the board was right also. It was a little confusing. Yeah. Oh.
Oh, wow. Good.
Oh,
So do you guys get to talk like this while you're online classes? Like otherwise you get to come to the class and talk to each other, right? Online you probably miss this.
Probably.
Or do you get to in other classes? How does it work?
No, I don't have. This is my only class that has actually a Zoom meeting during the class time.
Oh, really?
All recorded?
Yeah. So I have like 4 in person and 3 are online. And
How many credit hours are you taking?
just 19 this semester.
Oh, just 9.
I'm trying to think.
No, my computer science one is the only one I have in person, and I'm really hoping she moves it online because there's the book that we have goes through everything she does. So I would rather just have her video up on a screen and then have the content that we're supposed to go through on the other screen.
Mm-hmm. Yeah. Well, I guess I have one other one. It's on Discord though. It's not on Zoom. So it's,
Really? Someone's teaching through Discord. That's cool.
I think he's a gamer.
It implies so, yeah.
He's a younger teacher. I think he might be maybe only a year or 2 older than me. So.
Okay, we're good. So sorry, you can go ahead and start.
Okay. You're missing Matt, I suppose, right?
A couple people, yeah, but
1, 2, 3, 4, 5. No, only one of us is missing. Yes,
more people walked in. Okay.
Yeah, I think Matt is. Yeah.
Yeah, while he told me he wasn't gonna come, I just finished a meeting with him actually before I came.
Okay.
He said, yeah.
Yeah, but the recording is there, I'm sure. They have the option to listen to it. Okay, I forgot to bring the file that usually has a lot due dates, but if I recollect correctly, Q due. What is this? 24 September 31st, I guess. Correct me if I'm wrong.
August.
Yes. Thank you.
I mean, I could do September.
Sure. Yeah.
Our whole first test is just based on the first homework.
Yeah. True. And there's homework 3 also listed. But this is not due, right? Or there is no due date to that, but it's relevant. It's not due, but it is relevant. So make sure you go over the material. It basically involves vector integration, divergence theorem, and the Stokes. Okay. And your midterm 2, midterm 1, I don't remember when. Any ideas?
September 11th.
And that is Friday, I suppose? Okay. So we have been trying to get used to working with vectors, especially with the gradient operator, when it acts on vectors and when it acts on scalars, how to use the vector identities there. And we pretty much boiled it down to, we were trying to suggest that there are 2 relevant, 2 identities, let's say. which takes us through most of the vector identities that we will need. And one is the gradient operator acting on the position vector. This is R, not gamma. So this is position vector. That's equal to the unit value. So this is think of it as a outer product, all possible combinations. So that's equal to 1. And the second is that this actually we proved, I suppose. And the second was R is equal to R hat. Actually, this was the extra credit problem. So maybe I'll go over it. So this two identities will let us evaluate most of the things. So let's quickly evaluate this. I think I roughly did it last time, but not finished it, I suppose. So this is gradient of R. This is magnitude. Remember, whenever I don't put the vector sign on top of it, it's understood that that's a magnitude of vector R. So this is I hat d by dx plus j hat d by dy plus z hat d by dz. And acting on magnitude, this is x squared plus y squared plus z squared. Right? That's the magnitude of R. Even though we are going to evaluate this in the rectangular coordinates, it's understood that this is independent of the coordinate representation. We could have done this in spherical polar coordinates or any coordinate and it's the same answer. What is this equal to? So this is I hat, and when you take the derivative, there's a partial derivative with respect to x. So first of all, the square root takes it to the denominator with a factor of half in front, and then when you differentiate the argument, it gives you 2 times x. The factor of 2 cancels out, and we have x over x squared plus y squared plus z squared. Same thing happens with j hat, except now this is y over squared plus y squared plus z squared, and this is j hat times z over. This is nothing but if you see the numerator, this is simply the vector position vector itself. And the denominator has all the magnitude of R in it. Let's see R. And we have vector R divided by R, which is nothing but R hat. And that's your second equation. And we can use this to do a lot of other quantities. Once we accept that, we can now say what is gradient of R squared. Right. So now you use the chain rule. We don't we don't have to evaluate this separately again. So instead, what we will do is treat this as a function, evaluate this with respect to R. So this will be the same as d by, maybe I should write it as a chain. Right? This is, so evaluate gradient. So think of this as d by dr of R squared. If you were to look at it in that form, and I use a chain rule, that means to say this is dr, right, d by dr, and then R squared over R. Right, this is the chain rule. First to differentiate with respect to R, and then differentiate R with respect to the quantity that you were working with. But that's this is nothing but the gradient of R itself, which we know, and this is an easy quantity to evaluate. That's simply 2 times R. So this is R hat, times 2 times r.
For that one, can you also do it the long way?
Yes, you can do it the long way, that's perfectly fine, but very quickly you realize that it's unnecessary. So any function of r, differentiate the function r itself, and then at the end, put in an r hat. So it's much simpler. It's okay, perfectly okay to do that, but most of the time, at least in the context that we are, or in most of the systems we'll be dealing with in this course, the expectation is that this part has been taken care of, so you can save time that way, especially in tests and other things. Even in an analysis, you can jump at a step. Okay. And this can go through in general. So we can say what about gradient of r raised to r cube, right? So this will be simply gradient of r, and then e by r of r cube. So that's r hat times 3r squared. That's clear. But this could be any function, so we can also do gradient of 1 over r, right? That's also a possibility. And that's become special now. What is 1 over r? What is the significance of 1 over r in electrostatics, let's say? Or gravitational physics, anyway? 1 over r? What about 1 over r squared? Where does this show up? In electrostatics? No? Go on. What is the relevance of 1 over r squared? No, you guys can cover.
It's when the distance is, the power of a force is weaker over distance.
Power of the force, right? So the Coulomb or the gravitational force, let's say magnitude wise, goes as 1 over r squared. There's a m1, m2 over r squared, right? So if it is charges, you would say q1, q2 over r squared, correct? That's good, and there is a direction associated with this. But let's say magnitude wise, it is this. But what about 1 over r? Where does that show up?
Potential.
Potential, very good. So, right, force is this much, so the energy associated with the force is 1 over r, right? So this is potential. In fact, this can be thought of as electric field. Force is charge times electric field, but energy is charge times the potential. So there's a 1 over r is the potential, and 1 over r squared is the electric field, and the gradient of this, derivative of this, will, or negative derivative of this, takes you from the energy to the force. That's a universal thing we'll see. So this is actually potential, right? And always remember energy, so the force is always equal to, for a conservative force, it is always the gradient of energy. So if you have a conservative force, it is always possible to identify a potential energy associated with it, and the connection between the potential energy and the force is the negative gradient. So that's a sort of a very fundamental understanding of how a system works. And in fact, one can interpret that the system actually is trying to reduce the energy. That's all the system tries to do. And in the process, when the system is trying to reduce its energy, that's change in energy, right? And that manifests itself as a force. So force is a secondary concept. It's the system is only trying to reduce its energy. In that process, it seems like it is moving, and it can be interpreted as a force. So that's probably the energy or potential, and gradient of that should be your force, which should be the electric field, right? So let's see if we do get that or not. So let's try to do this. Again, we do the same idea, chain rule. So write this as gradient of R in the numerator and derivative with respect to 1 over R. And just so that we can interpret it as the electric field, let's put a negative sign in front of it. Because this force has this negative sign in front of it. So that's, we're just doing examples here. So that's negative of 1 over R is a gradient of the magnitude of R, which is R hat. So there's minus sign there. So it's minus sign, that is an R hat. And derivative of 1 over R is minus 1 over R squared. So it's minus 1 over R squared. That's nothing but R hat over R squared. And you'll recognize this as the electric field, except for the units in front, right? There's a 1 over 4 pi epsilon that sits in the front if you're working in SI units, but we'll come to that later on. So that's your electric field. So this becomes very convenient if we accept that this is equal to R hat. And it's not that we accept it, we have shown that once you've shown it, you just remember it. So these two equations, just these two alone, takes you a lot of, like saves you a lot of effort as far as calculations. So that's good. So what about, we can do the same thing with other terms, right? So let's say gradient of 1 over R squared. Examples here. That's equal to gradient of the magnitude of R and d by dr. So that's minus, this is R hat, and it's minus Q over R cubed. And so on. So you can do various problems of that kind. Here now, we want to specifically talk about the following situation. So now let's say this is all scalars, right? Given a scalar, we know how to act on it. But now let's try to act on vectors. And when we act the gradient operator on a vector, we are worried about whether it is a scalar product or a vector product. And let's specifically do a divergence of a vector. So let me go to the other board actually. So let's evaluate divergence of R hat over R squared. And we brought this up in some discussions earlier. And let's do that more carefully. This is having the information of Gauss's law, because this has the electric field, right? This is of the form of the electric field. So let's see what that is equal to. Actually, going back to the earlier board, what we were doing, just as an extra credit problem. Extra credit. So evaluate gradient of 1 or r raised to n in general for n equal to say n being integer, right? N is integer. That means it can be negative also. So -3, -2, -1, 0, 1, 2, 3. Right? Any of those. So for general, what is it? Keep an arbitrary and try to. That's actually a simple expression. Back to what I'm suggesting here. So notice what I know to do is I know how to take a gradient of a position vector. That is r hat. This is 1, and this is gradient of r. And we probably pointed this out last time. What is, as a corollary, this implies that what is of vector r? What's the gradient operator? Notice this doesn't have any operator in between, right? What is the divergence of the position vector?
3.
3, right? Because this should be interpreted as I hat plus j hat plus k hat. So this is 3, right? That's a simple corollary that comes about. We want to write this in terms of r vector r so that we can use these relations. So let's write this as dotted with vector r over r cubed. Just so that I can use those relations. So that's equal to, I can hit on the numerator. That's 1 over r cubed, or I can hit on r cubed, right? So it's plus gradient of 1 over r cubed dotted with vector r. That's the two terms, basically distribution of the differential operator. And now we know that this is 3, because we just now said that, so that's 3 over r cubed. And this, we just now did that, correct? So this is r cubed, so I can say this is plus gradient of r times d by dr of r cubed, oops, 1 over r cubed. Dotted with vector r. Dot, so this dot goes with this vector here. So this is a number, a scalar, that doesn't matter. So this dot connects this vector with this vector. That was r hat. Let me write this again. 3 over r cubed plus r hat, and this is minus 3 over r raised to 4, and that is a vector dotted with vector r. R hat dotted with vector r gives me an r itself, so this seems to be 3 over r cubed minus 3 over r cubed, which is 0. Except one might argue, one might be, if you're a little more careful, you might say that, oh, maybe this is not okay when r is equal to 0. When r is equal to 0, just at that point, everywhere else this has to be 0. But when r is equal to 0, one might worry that, oh, there's an infinity, minus infinity. Is that well defined, or is this okay or not? And with that caveat, so surely r not equal to 0, this is surely correct. It is almost everywhere in space except at one point. And remember that this is the electric field we are talking about, so it's connected with a point charge. So at r equal to 0, there's a point charge sitting. So, so how can we do this? So this is where your integrations comes in. So if this is really true, so let's actually, so this is 0 everywhere, right? R equal to 0 everywhere in space. So what will I get if I integrate everywhere in space of this function? So let's say this is a function, right? F of, this is a scalar function. That's f of r. And this is all space. Or let's say a finite volume of that. Let's all do it on a sphere. Sphere of radius r. And it is clear that everywhere on that sphere, this function evaluates to 0, except right at the point 0, which we don't know, right? It seems like it blows up, but maybe it cancels out. And for that point, I should actually ask you, so suppose you have a function that goes like this. This is a function. You have a point B, and let us say I remove one point out of it. So this is slightly tricky. That's an open circle. Open circle means that I remove one point out of this function. So this is an x-axis. That's your y-axis, which is function f of x. And I just remove one point out there. This looks like a big point, but that's just one point, right? One point on a number line is very strange thing, because right next to it, there are very close to it. It's a dense set. That's what you say. So we can define this in a certain way, right? So let's say this is 0, or let's say this is point C, and this is C minus delta. That's C plus delta, correct? And let me define an integral a to b dx f of x. And the question is this equal to limit delta tends to 0 of a to c minus delta plus c plus delta to b of dx f of x. Right. So hopefully this is clear what I mean. So first I do the whole integral, and the second is I go in steps. I go from a to c minus delta and then c plus delta to b, which means to say it actually raises the question, what is this area all about? Right? That's the quantity that we are missing. So or we can say, what is this c minus delta, which is c plus delta dx f of x. So what is that equal to? Anyone? In the limit delta tends to 0. Any comments? What do you expect it to be? An integral is the area under a curve, right? So this will be this area, right? What will that area be if I take this limit smaller and smaller? What will be the area of a rectangle of height h? Let's say this is 2 times delta, and the limit delta tends to 0. So area is 2 times delta times h, and the limit delta tends to 0. What will it be?
It'll be 0.
Yeah, it should be 0, right? So yes, so it will be 0, right? And the limit delta tends to 0 of this area, that's equal to 0. That's correct, right? This is this area of a rectangle should go to 0. That's good. So this is equal to 0. Is there now the question is, that's surely 0. I agree with that. But is there a possibility that that's not 0? Can we think of,
Function evaluates infinity at that point.
tell that again, Christian? I couldn't hear you.
Oh, I said if the function evaluates to infinity at the point C.
Exactly. So this is correct. If delta goes to 0, this is 0 if h is finite. Right? If h is 3, it could be as big as a million, billion, how much ever big it is, as far as it is finite, something multiplied by 0 will give you 0. But if this was infinite, then you have a 0 over a 0 possibility. And then there is a chance that there might be some finite value, some 0 divided by 1 over 0, which is probably infinity. Then you have to be careful with those limits. So this is correct, equal to 0 if f of c is not infinity, is not like infinity is not a number as such, so it should be, does not approach to infinity at that point. Otherwise, we don't know. Right? So in general, it is true that it should not be equal to it should be equal to 0. Now, if we were to take this to this equation here, this is equal to this if we can actually remove a point and still the integral is fine, as far as at that point it does not go to infinity. So that's an important factor. Now, we are doing an integral of a function which is 0 everywhere. So there is a possibility that at r equal to 0 something happens. If that at r equal to 0, even if we don't know what that value is, it should not contribute unless it is infinity at that point. If it's infinity, then we don't know, because then there is a small tiny volume element multiplying a very large quantity at that point, and there might be issues. So let's evaluate this and see whether we really get a 0 or not. That will at least tell us whether at r equal to 0 this is infinite or is it finite. Right? That will tell us that information. So let's do this integral, and this integral is actually e cube r, and this is a volume of radius, sphere of radius r. So let me just write radius r here, and this is gradient or divergence of r over r cubed, or r over r squared. And probably you guys remember the divergence theorem. What does the divergence theorem say? Remember? So let's try to remind ourselves of some integral theorems. So let's say we have a function defined from a to b, dx, and let's say this is derivative of f of x. What is that equal to?
B minus A.
B minus a. No, try again. Very similar, yeah. I think you're thinking correct probably because you said b minus a, but something else?
F of B minus F of A.
Minus f of a. So this is an integral, that's a differential, they cancel each other, right? but except at the boundary. So it's only the boundary that evaluates to. So this is equal to f of b minus of f of a. So if you have a differentiation of a function and then you integrate it, integration pretty much cancels out the differentiation, but then at the boundary it survives. So the functional value only at the boundary survives. This is pretty much like the work done by a force, right? Work done by a conservative force. So if this was the potential energy, it is the change in potential energy that matters. It does not matter. It doesn't matter how you go. So here, what we are actually doing is this is a line X, and you're going from point A to point B. There is only one way of going from here, but actually you could have actually gone all the way to there and then come back. Right? Even if you go put in a C there, it doesn't matter. So it is independent of the path. But in one dimension, independence of path is not very rich, you can say. There's only one way you can go. But now let us say that you're actually on a plane, and this is actually a line integral. And this is a gradient operator, and that's a dot. So what we are actually doing here is this was one dimensional, now we are two dimensional. This is X, and that's your Y, and that's your DL. So it's a small line element DL. And now you have to go from point A to point B. These 2 points are specified by vectors. These 2 boundary points on that line are given by vector A and vector B. And this is a 2-dimensional plane, so the function is at every point there is a functional value. I cannot show that, so if it was 1-dimensional, then I use the 2nd dimension to show the functional value. Here, at every point in this 2-dimensional or 3-dimensional space, there is a value for the function. And let me define that to be f of x. This is not the same function because this is 1-dimensional function. This is a 3-dimensional or 2-dimensional function. Is that a well-defined integral? Actually, no, because I haven't. This does not give you this information of this curve. So I have to give you one more information, and that's the path. I have to tell you along which path do you want to integrate. And that's what you will do for work done by a force. You will usually take the path, right? That's only then it's a well-defined quantity. Unless it's a conservative force. And if this was a conservative force, that is what it is, if you can write it as a gradient, then again, exactly like the earlier statement, because the derivative and the integral cancel each other, this is equal to f of b minus f of a. Any questions there? That's nice. So notice if you have a gradient operator, so this is like a 1-dimensional integral, then it is actually the value of the functions only at the boundary survives. So these are at the boundary survives, this survives at the boundary. So now let's take a leap. So this is line, we can actually do a surface, or let's jump to a surface. So this is a surface integral. Surface has a direction. What's the direction of a surface?
Normal to the surface.
Always think of a normal direction to the surface, and every tiny element you have a surface element, and that's normal to that. So del dotted with similar thing, but now we are going to write it as a curl. So this is a curl of some quantity. So let's write this as b. So there's some function of x. Now, this is an area element. This was a line element. So this is an area element. And that means to say that I have to integrate this on a surface. So this is integrated on a surface. When you integrate on a line and there is a gradient operator showing up, they cancel each other, it survives on the boundary. What is the boundary of a surface? What's the boundary of a surface? For example, if I tell you it's a surface is a disk, what's the boundary of a disk? So if I have a disk, its boundary is a circle, right? So this is its boundary. Right? So whatever, there is a curve that encloses the surface, and that will be considered the boundary. And always, if you have a surface, it will have a closed curve bounding it. If you can imagine any surface, you will always have a closed curve bounding it. In this case, it's a circle bounding a disk. And this is now what is called the Stokes theorem. This is equal to always a closed integral of dl dotted with b. Notice what is it saying? Even though this is an integral, this is a boundary, right? Whatever this was is equal to the function at the boundaries. So here this was evaluated on the whole surface, evaluated on the boundary. But since the boundary is actually continuous, it's not just 2 points, you have to actually integrate over the quantity there. And this is a closed curve. So this is a line integral. Okay. So line integral gets the boundary of a line are 2 points. Boundary of a surface is a closed curve. And next you can do a volume, right? So this is a volume. This is a volume. A d cube of 3 integrals. That means you're integrating over a volume. And you can do divergence of some vector field. So let's call it E. Idea is that this is electric field, that's magnetic field. So what is the surface of a volume? Or what is the boundary of a volume? Like if you have a finite volume, it will always have a surface enclosing it. Right? Like a disk is enclosed by a curve. A surface is enclosed by is bounded by a curve. A volume will always be bounded by a surface. And so that's your divergence theorem. It tells you that instead of doing this volume integral, it survives only on the boundary. So this is dA. Now this is a closed surface. So this is the surface bounding the volume B and dotted with electric field, right? Evaluated at the boundary. Notice there's a disk evaluated at the circle. If this was a sphere, evaluated on the surface of the sphere. So this is called the divergence theorem. And this is called the Stokes theorem. I expect you to have seen this somewhere or the other. This is the content of homework 3 if you want. Do some examples in homework 3. And this is basically the idea, this idea generalized to higher dimensions. So what can I do with this? If this is true, I can evaluate this on a surface. This is on the surface of a sphere. That's dA. dotted with r hat over r square. If this is the surface of the sphere, sorry, this is r hat. If this is the surface of a sphere, this will be 1 over r square. This can come out. So this is 1 over r square because this is evaluated on the surface of a sphere. It's a constant on the surface of a sphere. It comes out. dA is dA itself, but its normal vector on the surface of a sphere is always in the radial direction, dotted with r hat itself. That's equal to 1. And whatever is left out is nothing but the surface area of a sphere. Once the vector sign is gone, then I'm left out with the surface of a area of a sphere. So this is 1 over r square times 4 pi times r square. That's the surface area of a sphere. R square exactly cancels out, and that's 4 pi. So what have I shown here? We said that this quantity, the divergence of r over r square, is 0 everywhere, except we were not sure about r equal to 0. But if you add up all those zeros, it seems like you get 4 pi. Right? The only way that's possible is that at r equal to 0, this is not a finite quantity. It has to be infinite, because otherwise you cannot add up all these quantities and get a 4 pi. In fact, at r equal to 0, that's a very special infinity. We actually know what kind of infinity can be, because this volume element, which is r cube, right? The whatever, how small does it go as r tends to 0? This has to be 1 over r cube, because when they cancel out, you should get a 4 pi. Right? So it's roughly know what that structure is, and we will talk about that more. So some function which is 0 everywhere and infinite at some point, that will be called a delta function, and we have to define it. But what we have now shown is that this quantity surely is not finite at r equal to 0. That's what we have concluded from these two statements. These are contradicting statements. Right? This is 0 everywhere, or not contradicting except for the fact that r equals 0, and this is 4 pi. So it's not trivial. It evaluates to 0 everywhere except for a point, but when you add up all those things, you get a 4 pi. So why is that? And we will define something associated. So we'll introduce what is called a delta function. That's all. I will stop at this point. Thank you. Any questions, comments? Okay. Thank you.
Thank you.
Thanks.
Bye, Christian.
Yeah, have a good